Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe and press the notification bell so that you will be updated of my future videos. I hope that my videos are helpful in your studies, not as students at present, but also in your future career. I hope that you will enjoy watching. So this is the first problem. By double integration method, compute the maximum deflection in mm. In this problem, the uniform load is 15 kilonewton per meter and the concentrated load is P is 12 kilonewtons. L sub 1 is 10 meters and L sub 2 is 3.6 meters. Modulus of elasticity 200 gigapascals and moment of inertia is constant at 250 times 10 to the 6 mm to the 4th. So take note that the maximum deflection might occur may be positive or negative. So there's a possibility that it is positive at C and the negative deflection will be somewhere between the supports. So first, let's solve for the reactions at A and B. Of course, AX is 0. So summation moment about B equals 0, clockwise positive. So RA times 10 plus 12 times 3.6. Then minus 15 times 10 times 5 equals 0. Solving for RA is 70.68 kilonewtons. Likewise, summation moment about A is 0, counterclockwise positive RB times 10, then minus 15 times 10 times 5, minus 12 times 13.6 equals 0. So it's up to you to verify that R sub B is 91.32 kilonewtons. You need check summation versus Y, and the value of RB is really 91.32 kilonewtons upward. So to set up the equation of the elastic curve, which is the moment equation, for this case, we can have one moment equation for the entire beam. So we extend the uniform load here in portion BC and add it with an counter upward load of 15 kilonewton per meter. So that's it. Our X is origin is A. So from origin to that section as X. So therefore, the equation is EIY double prime, equation of the elastic curve, is RA, which is 70.68 times X, plus RB times quantity X minus 10. So this is X minus 10. Then plus 15 times X minus 10 times X minus 10 over 2, or plus 7.5 times X minus 10 quantity square. Then minus 15 times X over 2, or minus 7.5 X squared. That's the equation of the elastic curve. Integrating once, EIY prime is 35.34 X squared plus 45.66 X minus 10 squared plus 2.5 quantity X minus 10 cube, then minus 2.5 X cube, then plus C sub 1. C sub 1 divided by EI represents the slope at A. So therefore, if we integrate this again, which represents the equation of the elastic curve, then definitely C sub 2 is 0 because at the origin there's no deflection. Or when X is 0, Y is 0. So we have EIY 11.78 X cubed plus 15.22 X minus 10 cubed, then plus 0.625 quantity X minus 10 cubed, 10 to the 4th rather, then minus 0.625 X to the 4th plus C sub 1 X. Of course, there's no C sub 2 because, as I said, the deflection at A is 0. Next, we evaluate C sub 1 by this boundary condition when X is 10, Y is 0. So 0 equals 11.78 10 cubed, then this is 0, this is 0, then minus 0.625 times 10 to the 4th plus C sub 1 times 10. So solving for C sub 1 is equal to negative 553. Then we can now evaluate the deflection at C first. So because this is one possibility of the location of maximum deflection, so we set X is 13.6 into this equation here for EIY. So 11.78 13.6 cube plus 15.22 3.6 cube plus 0.625 3.6 to the 4th then minus 0.625 times 13.6 to the fourth, then plus negative 553 times 13.6. So evaluating for delta C is EI delta C is 1544.976. The unit is kilonewton meter cube. Then let's compute delta C in mm. So we convert kilonewton meter cube to Newton mm cube by multiplying this by 1000 to the fourth. And E is expressed in megapascals, 200,000 megapascals, or 200,000 Newton per mm square. And the moment of inertia is already in mm to the fourth. So the units in the denominator is Newton mm square. The numerator is Newton mm cube, so the net unit is mm. So delta C is equal to 30.90 mm, and because it is positive, it is upward. Next, for maximum deflection between the supports, since the slope of the tangent at the lowest point is horizontal or 0, then we set EIY prime, because this represents the slope, to 0. And we ignore the second term, which is x minus 10 squared, because we expect that the value of x is less than 10. And so this is negative, this is also negative, so we ignore these two. So 0 equals 35.34x squared, then minus 2.5x cubed, then minus plus C sub 1 or minus 553. So using your calculator, there are 3 roots here, but only one is possible. The other two are either negative or absorbed. So the value of x is 4.892 meters. So substitute into this equation for EIY or deflection, 11.78 times 4.892 cube. Then this is ignored because the value in the parentheses negative. Minus 0.625 times 4.892 to the fourth, then minus 553 times 4.892. So delta is negative 1684.1. This is greater in magnitude than this, so definitely this is the maximum deflection, which is negative. So in our experience there, we multiply 1000 to the fourth numerator, then you just express E in megapascals. Then delta is negative 33.68 mm, so therefore the maximum deflection is negative 33.68 mm, and it occurs between the supports, particularly 4.892 meters to the right of point A on the beam. For our second example, for the beam shown below, the uniform load is 300 Newton per meter and the beam is rectangular in shape, 75 mm wide and 125 mm high. Modulus of elasticity is 9.6 gigapascals. Determine the maximum slope in degrees and the maximum deflection in mm. Use only area moment method. The following are the data. A is 1.2, B is 1.0 meters, and C is 0.3. So because we are required to solve this problem by area moment method, so we select this fixed end, fixed wall as our moment center. But we substitute the values of the data, A, B, and C, and the load. So first, let's have the moment diagram by parts. So we compute the moment of this uniform load at B first, then at A, so that the resulting moment diagram would be easy to compute, especially the area. So this is the moment second degree, because this is 0 degree, so the moment curve would be second degree, 0 plus 2. So 300 times 1 times 0.5 is 150 over EI. The unit here is Newton 150 Newton meter, the numerator. Then at the walls, so 300 times 1, so 300. The distance of the centroid to the wall is 1.7. So 300 times 1 times 1.7 is equal to 510 over EI. Then we divide this moment diagram into known areas like that. and to make this triangle. So 510 minus 150, the height of this triangular portion would be 360 over EI. So we draw the corresponding elastic curve. This is the expected elastic curve. And so the maximum deflection occur at D, because the portion CD is straight, because CD is unloaded, then the maximum slope occurs at C or at D. They are equal because this is straight. So this is deviation of C relative to A, and this is the maximum deflection, which is deviation of C relative to A plus this portion here, which is 0.3 of theta maximum. So because this is theta maximum, by the way, is the theta between A and the tangents between A and C. So remember, EI theta AC is the area between A and C, and it is the change in slope between the tangents at A and the tangent at C. But the tangent at A is horizontal. That's why theta AC is automatic theta max or theta C, which is also equal to theta D. So again, this distance, vertical distance from the tip of deviation of C relative to A to the tip of this elastic curve at D is 0.3 of theta max. Why? Because tangent of theta max is theta max opposite over 0.3. So that's why it is 0.3 times, the opposite is 0.3 times theta max. So EI theta AC is the area of between the two curves. So beginning with this spandrel, it is, beginning with this trapezoid, so it is 1/2 or 0.5 of negative 510 plus negative 150 over EI. Then distance between them is 1.2. Then plus area of this spandrel, 1/3 of 1 times negative 150 over EI. So that would be the theta AC or theta max. EI theta max therefore is negative 446 Newton meter square. So we just convert this to Newton mm square. E must be in megapascals, so 9.6 thousand megapascals, and I is in mm to the fourth, so that the resulting unit would be in radians. Then we multiply by 180 degrees divided by pi radians. So negative 446 times 1000 square to convert it to Newton mm square, then E in megapascals, which is 9,600 megapascals or Newton per mm square, then I is BH cube, 75 times 125 cube over 12. That would be in radians times 180 degrees over pi radians, so that would be in degrees. So theta max is negative 0.2181 degrees. So negative means clockwise. Then for the maximum deflection, so we have deviation of C relative to A plus 0.3 of theta max, where deviation of C relative to A is the moment of these areas with respect to C. So these are the location of centroid. So for the rectangular area, the distance is 0.6 plus 1, so 1.6. For the spandrel, this is 1 over 4 or 0.25, so its distance from the right is 0.75. And for this triangle here, this is 2/3 of 1.2.8 plus 1, so 1.8. So EI division of C relative to A is beginning with the spandrel, negative 1/3 of 1 times 150, negative 150, then moment arm 0.75. For the rectangle, it is 1.2 times negative 150, then times 1.6. Then for the triangle, it is 0.5 of 1.2 times negative 360, then times 1.8. So computing for that division, it is equal to negative 714.3 Newton meter cube. Then the maximum deflection is negative 714.3 over EI plus 0.3 of theta max, which is negative 446. So that theta max is negative 848.1 Newton meter cube. So we convert that to Newton mm cube. So we just multiply 1000 cube. Then E is 9600 megapascals or 9600 Newton per mm square. Then moment of inertia in mm to the fourth. So the resulting unit is mm. So delta max is equal to negative 7.237 mm. So that's it. And finally, for this third problem, we solve this by the conjugate beam method. The vertical deflection at C in mm and the slope at C in radians. Modulus of plasticity is 150 gigapascals constant, and the value of I here is 400 times 10 to the fourth. But there are three segments of different moduli of inertia, but the I is 400 times 10 to the 6. So let's compute first for the reactions. So let's prepare the moment diagram by parts. So let's make C as our moment center. So call that AY, AX is 0, then RD. Summation moment at D equals 0. So AY times 15 minus 60 times 10 minus 40 times 4 equals 0. So AY is 152 over 3 kilonewtons. Likewise, summation moment about A equals 0, counterclockwise positive. RD times 15 minus 60 times 5 minus 40 times 11 equals 0. So R sub D is 148 over 3 kilonewtons upward. So because we make C as our moment center, so AY 152 first times 5 over EI. So it is 152 times 5 over EI is 760 over 3 over EI, just to the left of B. Now, just to the right of B, the moment of inertia is 2I. Then we divide 760 over 3 by 2. So it becomes 380 over 3 EI. Then the moment of AY about C is 152 over 3 times 11. Then divide that result by 2 because the moment of inertia for up to C just to the left is 2. So 836 over 3 after we divide the result by 2. Again, it is 152 over 3 times 11, then divided by 2 because the I is 2. So 2I. So 836 over 3 EI. Then the moment of RD is 148 over 3 times 4, because that's 4, then divided by 1.5. So that the result is 1184 over 9 EI. Then the moment of the 60 kilonewton load is 60 times 6, 360, but because the moment of inertia is 2I divided by 2, so it is only 180 over EI. Then we want to solve, we want to modify the supports. The supports will not be changed because these are end supports. So, and there is no interhinge in between, so the end supports remain the same in conjugate beam method. So it is still a pin and a ruler there. Then this trapezoid is divided into two triangles in this manner. So let's apply theta D. That's the positive direction of shear. So that's theta D positive. Theta A is upward here on the left. Then we sum up moment about A equals 0 to solve for theta D. So these are the locations of the centroid. Remember that the forces here is upward for above this beam and downward for below. So theta D times 15, summation moment about A 0. Then plus this load, the moment of this load is 0.5 times 6 times 180 over EI. Then the moment arm is 2/3 of 6 is 4 plus 5. So 4 plus 5 is 9. So 0.5 of 6 times 180 over EI times 9. Then minus this loading, 0.5 of 5 times 760 over 3 EI. Moment arm is 2/3 of 5 or 10/3. Then minus this small triangle here, 0.5 times 6 times 380 over 3 EI times 2 plus 5 is 7. 2 plus 5 is 7. Then minus this, quantity 0.5 times 6 times 836 over 3 EI times moment arm 4 plus 5 is 9. Then finally, minus this load, 0.5 of 4 times 1184 over 9 EI, then 4 thirds plus 11 is 37 over 3 meters. Then equals 0. Then we can now solve theta d. Theta d is expected positive because the slope at d is up to the right. So theta d is positive 712.01 over EI. Then having found theta d, let's consider CD. Let's apply the positive shear or positive theta C, which is downward, and the positive deflection or moment is clockwise. Positive is clockwise because it is left section of section B. So theta C is upward, and because it is left, it should be upward, then clockwise delta C. That's delta C. So to solve for theta C, we simply sum up forces vertical considering CD. So theta C plus 1/2 or 0.5 of 4 times 1184 over 9 EI minus theta D or equals theta D, which is 712.01 over EI. So solving for theta C is 448.899 times 1000 cube to, because the unit is kilonewton meter square, so times 1000 cube to make it Newton mm square, and divided by E in megapascals, 150,000 megapascals, then I 400 times 10 to the 6. So theta C is in radians 0.007482 radians. Then for delta C, summation moment about C equals 0, clockwise positive, so delta C plus theta D times 4, so delta C plus theta D, which is 712.01 over EI times 4 equals moment of the triangular load 1/2 or 0.5 of 4 times 1184 over 9 EI times 4 thirds. Solving for delta C is negative 2497.225 over EI. Then the numerator is kilonewton meter cube. Denominator is, we have to convert E to megapascals and I in mm to the 4th. So we simply multiply the numerator by 1000 to the 4th and the denominator E in megapascals and I in mm to the 4th. The resulting unit would be in mm. So delta C is negative 41.62 mm. So that's it. And I hope that you were able to understand the solution. And please watch out for my future videos. Thank you for watching.